back to week 5 of Sigma lectures. Are you guys ready? So there's good news and there's bad news. The good news is this week is really easy if you've thoroughly kind of watched the previous week and you kind of understand the flexure stuff. Because we're just going to do examples and whatever of the flexure stuff. It won't be too bad. The bad news is if you don't remember that, then we're in trouble, right? Anyway, so I've got 2 examples for you. These are from, I believe both of them actually are from my assignment back in 2023. So one is a custom section, and so it's like basically question 1, question 2. The first one is basically we have a rectangular hollow section, and it's a custom section, and we want to find MS and MB. Do you guys remember what those are?
Member slender, member beam. I mean, section and moment section and moment beam.
Yeah, that's pretty much it. Yeah. So this is the section capacity, and that's the capacity when you consider the buckling of the beam, the lateral torsional buckling. This kind of ringing a bell. And then we also have a weird section which will look like that, I think. So it's like a circular hollow section with 4 plates sticking off of it. But for this one, there's no beam that they show you. So we just need the section capacity. Does that make sense? Because to get the member capacity, you kind of need the information of what the beam will look like. Because then you get like what the effective length is and all that, and what the restraints look like. Make sense? Okay, let's just get started. Okay, so what I've done here, you can probably immediately notice, is I've crossed out this part. In the assignment, they wanted us to find the shear capacity of the beam as well, but we're not going to talk about that until week 7. But there's quite a bit of information here to take in. Let's look at the blue highlighted stuff first. So it says it's grade 300, and then it's also heavily welded. So these will be things that we're just going to have to keep in mind. And it's like that information that's provided in the question that we'll need for some of the tables. And then it also says the beam has no out of plane rotational restraint. That's to do with another one of the table factors, KR or something like that, KT maybe, I don't know. One of those K factors for finding the effective length. Okay, and then
does that mean we also have to check the rotated version?
What do you mean, sir?
Like you have to do it again, but 90 degrees.
Oh, so okay, basically our section is a rectangle, right? So it's not a square. So what you mean is we just check X bending, right?
We have to do Y though.
We don't have to do Y, and that's just because the question says we only need the X-axis bending.
Oh.
So what we're actually doing is we're finding MSX, MBX. You know what I mean?
Do we ever need to find MX, MSY? Next question.
In beam columns. Yeah.
But this is just a beam.
This is a normal beam. So basically for a column, let's put it like that. Because a column, imagine this is like a rectangular hollow section for a column. It could bend in the major direction or the minor direction. But for a beam, we just orientate it to bend in the major direction, right? So we don't really care about MSY or MBY. Yeah. Okay. Let's quickly look at this information. I'm gonna ask you guys a couple of things, right? So in the top right, that's what our section looks like. So they've given us information about that. They've also given us our They've also given us our, what's it called, free body diagram, and it also says like F, L, and P, and you know all that shit, right? This stuff. Do you guys remember what F, L, and P stand for?
Fixed lateral thing and pin. Lateral restraint.
So it's not to do with the supports, because when you say like fixed, that's like a fixed support, that's like a pin support, right?
Mm-hmm.
So what makes a support a support? Like these ones. It's something that can't move, pretty much, right? So when we consider like that a column, for example, is fixed to the ground, we just assume the ground point isn't moving relative to our entire system, right? But what we're doing instead with, because you can see here, this is like a roller support, and then this is like a pin support and all that. What we're saying with the F, L, and P is this is about lateral restraint. So it's about restraining it from moving left and right, basically. And that's important because of lateral torsional buckling. So if it's restrained from laterally buckling, it won't do that. Do you know what I mean? Yeah. And so when we're talking about effective length, we're considering points that are restrained from lateral movement. Do you know what I mean?
I see.
Not really the same as a support. So like you can see here, L, like that doesn't have a support under it.
But it's a laterally restrained.
It's laterally restrained, right?
Then what does F stand for?
F stands for fully restrained.
And P is partially restrained?
Partially restrained, yeah.
And that just affects the numbers used in the table?
Let me... No, I can't really... This is going to take me a second, but I'm going to find it, right? I'm going to show you guys... I know this isn't on the screen for you guys at the moment, but I'll bring it up. I think it helps to see what these actually mean, because we actually have... Oops. We actually have time today, I feel, because I don't have to go through that much content. Okay, so what I'm going to do... Oops. I'm going to share screen so that you guys can see it on the TV. So I'm gonna... Oh, now there's multiple people sharing screen. Fucking hell, sorry. Messy. Okay, you see that? Oh, actually, I'll show you the whole thing. Do you see how it says detail 1, 2, and 3 here? Okay, so I know this is a lot to take in right now, but this is one of the questions. That's like given as like a workshop question or whatever, right? And so, firstly, the actual supports. Do you see how many there are?
2.
There's 2 actual supports, right? Here and here. Okay. Next, detail 1, right? What type of support do you reckon that is in real life?
Yeah.
F, L, or P?
Wait, say again.
Do you see detail 1 here? Do you think that's an F, L, or P restraint? Yeah. So it's fully restrained from laterally moving. So imagine these are like beams that are going in and out of the page, and they're effectively acting as like supports, but like sideways. So you assume they don't really like, they're not flexible. Yeah. They're stopping the beam from buckling that way, right? Okay. Next, detail 2, right? Would you consider this P or L?
P.
L.
Okay, think of it like this, right? Firstly, what is the bending moment diagram gonna look like? I'm gonna overlay it. I think you drew it right actually in there.
Wow.
Fuck. I'm not gonna draw this very well. Can I do it with my finger? Oh, I can. Let's go.
Oh, that was good.
Oh wow, that was really good.
That's
And-
so good.
So that's a bending moment diagram, right? And do you remember what we were saying last time with oh no, this isn't gonna work very well. Okay, do you remember what we were saying last time with compression, critical flange? Okay, so firstly, which parts are simply which parts are supported from both ends, and which parts are cantilevering in this particular question?
The middle is simply supported.
Yeah. And then
The outside.
Those are cantilevering, right?
Mm.
So for a cantilever, let's just start with the middle. For the middle, is it tension or compression is the critical flange?
Looks
Wait,
like.
what do you, wait. Stop, don't speak.
Don't speak. Do not say a thing.
Say again. Which part is critical flange?
Yes, for the middle part.
Wait.
Compression flange or tension flange?
How do you know?
What do you know about lateral torsional buckling? Where is the critical flange? Like, where's it gonna buckle out from? The compression side or the tension side?
No.
Do you remember that when I was doing that with the stick last time?
Yeah.
I was like racking it the direction that it normally does with like normal gravity loads, and it buckled from the top, right? Like it looked like it was gonna buckle from the top. That's the compression flange, right? Because the compression flange is the one that wants to basically Euler buckle, but not really Euler buckle. It's just the compression wants to like go out from the minor axis, right? Whereas the tension wants to pull and straighten out. So the tension is the bottom that wants to straighten out, right?
So it's in compression.
Compression is the critical flange. That's the one you need to restrain, right?
But it's not going out like this, it's going down like this, right?
Oh, it's going down, but do you remember what was happening with that stick? It was also going out to the side, but only from the top side, right? I think it would help if I showed
to
you.
say tension can't ever buckle.
No, because I'm going to show you why in a second.
What?
Sorry, yeah.
Wait, I don't understand like the diagram.
Oh, forget about the diagram for a second.
Oh,
Just
I
remember
think
that
that's
stick
why
thing.
that's
Do you remember like when I was bending that stick? What
Just-
happened is the middle of the stick from the top fell outwards,
So like this.
but only the top, so it rotated. It rotated.
Imagine
From the compression side, right? But compression is like that, but I did that. I'd like bent it, right?
Yeah.
What happens is only the top half of it is in compression, and the bottom half is in tension, right?
Yeah.
Of that stick.
Yeah.
And so the top half is the part that wanted to buckle out.
Oh yeah.
So what we want to do if we want to stop a lateral torsion buckling is we need to restrain that.
Oh,
That
just
flange.
the top part.
Yes.
The top flange.
But it depends, because it depends on which part's in compression. Right.
Oh. As in, but you're saying the top is in compression, so wouldn't you restrain the top?
Yeah, so actually what's happening is let's talk about that again. So these are restraining the top, correct?
Yeah.
Okay. But what
Is
about
that like one big beam?
yeah,
Oh.
like we're running left to right. Yeah,
I
that's a
thought
beam.
it was like two views of. Okay, well, don't worry, just continue.
Okay, but we can agree that it's restraining, like those detail 2s are restraining the critical flange, right?
Yeah.
Hey, what about detail 3? It's restricting the bottom, but it's a cantilever, right? So for a cantilever, do we consider the critical flange as the tension side or the compression side? It's only for a cantilever that we consider the tension side, because it's that thing I said, right? So in the videos, it falls out from the tension side. It doesn't really make any sense in my head, because like compression is the thing that like causes something to buckle, right? Like laterally torsional buckle as well as a Euler buckle. But for some reason, cantilevers buckle from the tension side. So, right, if we're considering like a diving board as an example of a cantilever, right? Is the top side in tension or the bottom side? Tension? Bottom's in compression, but the critical flange is the tension side, right? Yeah. Yes. So, does that mean detail 3 is restricting anything? The critical flange?
So it could just so in
Can
the
you-
cantilever, the bottom is in compression.
Yes.
Okay.
But
The bottom you need to restrain.
no, because for cantilevers, the tension side's the bad side.
Oh,
Only for cantilevers.
because like it's gonna break from there.
Yeah.
Wow.
Yeah. So when you put bending on a cantilever, it will fall out from the top,
Okay.
which doesn't really make any sense because it's in tension, but that's just the way life goes.
But then on that diagram they put the restraints on the one.
Correct. So it's not restrained
Oh,
because you're restraining the wrong flange.
that's a bit silly.
It's a little bit silly, eh? So, here's what it looks like. So, where you see detail 3, it's actually, we don't consider it as a restraint at all.
So it's just.
So there's nothing,
Oh.
because it's restraining the wrong flange.
Oh.
At the very ends of the cantilever is always U, which is unrestrained. So that's like the end of a beam. Detail 1 was F, because it's fully restrained, right? And then all of these were laterally restraining. Now, the thing is, there's actually there's not like a really, really good way to pinpoint the exact difference between F, P, and L. It's like, there's a lot of like designer handbooks, but it's not explicitly in the code. So, yeah, it's kind of hard to translate this exact schematic into F, P, and L. But the thing is, in your questions, you're going to be provided with F, P, and L, and where they are. So you won't, most of the time you won't need to. No, but I just want to show you what it actually looks like, because F, P, and L are just cryptic letters. They're not really like gonna. Yeah. So I'm just showing you one example, and I won't show you more examples. But yeah, hopefully that makes sense, right? Any questions? I just wanted to show that because I figured that's pretty important. Okay, so with that said, this is probably like, do you remember that detail which was like the equal angle that was like up here, laterally restraining? That's probably like what that detail would look like in real life. So it's because it's flexible, it's partially restraining the lateral movement on the compression side, right? And then these are like full restraints or something, so there might be other beams coming in and out of the page or something. I'm not sure what a good example of the partial restraint is, to be honest.
Maybe like a partial beam.
A partial beam? Yeah.
Yeah.
I don't know. I don't want to draw something incorrect, but yeah, just pretend there's something else that's like partially restraining. Yeah. There's like proper definitions and stuff in the code, but yeah, anyway. Okay. Sorry, that was a big tangent, but what do you know about the shear force diagram? Like what kind of information can you deduce?
Max shear.
Oh, sorry, you can't see it right now. What the fuck? Sorry. I've kind of been trolling. Stream, watch stream. Okay, sorry.
Ah.
Yeah,
yes.
that's what I'm talking about. Yep. So, yeah, from this shear force diagram, what can we kind of deduce here? Like, this is all the information you provided, but we're doing a flexural design question, right? So what's more important than the shear force diagram?
Bending moment.
So just from looking at the shear force diagram, what can you tell about this system?
It's gonna become like zero. It's symmetrical.
It's symmetrical, that's true. So we don't have to check the entire beam, we can kind of break it up using symmetry. Okay, what else? What's the reactions?
120.
So each of these are 120, right? What's this one?
400.
Yeah. Okay, anyway, you can do it however you want to figure out the bending moment diagram. I've done it like this. Oh, and a distributed load, right? Because you can see this is like kind of falling. Mm-hmm. So that implies there's a UDL on there, right?
Mm-hmm.
So you just do this difference in the force at that point, and then divided by the length, right?
Mm-hmm.
And you can find the distributed load.
You just know it's zero moment at the edge.
Because they're pins, right?
Oh, yeah.
Pin supports.
Right.
Yeah. Only there's only two scenarios where it won't be zero moment on the edges, and that's a fixed support, or if you have point moments again. Turning it. Anyway, so yeah, I just made a bending moment diagram. You can do it using 1300 methods, but the idea is actually you'll see why we need the bending moment diagram later. Okay, next is steel properties, right? So here's the order that I like to find it for a custom shape, right? The first one is yield stress. So that was not too bad because it's based on plate thickness, right? And it's in like table 2.1, I think, in AS 4100.
Yeah.
Okay, but then remember how we talked about effective section modulus for edges last time? So it's hard because there's 4 steps basically, right? You have to classify it, like whether it's a slender section, compact section, non-compact. Then you have to find IX, right, which is the moment of inertia. Then you have to find what Z and S are, and then you can finally get ZE, right? Those are all the parts you need. And we also need the moment of inertia about YY. So we need that for the formula later that's going to be used for reference buckling moment. So reference buckling moment is AIDS, just in general, but especially for a box section, like a rectangular poly section. Yeah. So you see how this is an assignment question. You're not expected to do this in exam, like all this shit, right? But I'm going to show you all the steps, right? First one's yield stress, so that's from the table 2.1, right? That one makes sense here.
Wait. Yep.
And it's based on thickness of the material.
Yep.
And our box has a thickness of 8, right?
Yeah.
So that's 8 for all the edges, right?
Yeah. Well, not the box. The component.
Yeah. But remember, this is made up of multiple plates. Oh, no, not really, actually. That's a bad way to put it. But yeah, like the thickness doesn't ever exceed 8 on any of the any of the elements, right?
Yeah.
Okay. But do you see how I've broken it up here?
1, 2.
These are the elements, and there's not 4 elements. There's only 2 unique ones, so we only have to do 2 calculations, right? Because we have the one that has the ratio of whatever that distance is to whatever this width is to this thickness, and then whatever this width is to this thickness. There's 2 ratios that we have to consider, right?
That's epic.
It's making sense too.
Yeah, it's making sense.
So we have to find the slenderness ratio of each element, right? Which is just plug into that formula.
Yep.
And then we have to compare it to the slenderness limit. We have to find the slenderness limit of each of the elements. Okay, so what I mean by that is this one, the yield limit. Slenderness yield limit. So it's from this column of this table.
Oh, I remember this one.
Okay, but I've got a question for you, right? Where did I pull this out of my ass from? Why am I going to these rows of it?
Because it says in the question, it's heavily welded.
Yeah, it's heavily welded, true. That says in the question. But we have this element for 1, I think I did, and this for 2. Yeah. Okay. But why did I do uniform compression for one of them, and why did I do compression at one edge and tension at the other?
Because one edge is in tension and one edge is in.
For which element, 1 or 2?
2.
Correct. Because if we consider the stress diagram, right, we're bending it, right? So here we have tension. Oh, sorry, we have compression, and here we have tension, right? And so element 2, one edge is in tension, one is in compression.
Yeah.
Okay, and then what about element 1?
That's in all compression. Uniform. Because
Uniform
it's so
compression.
Small,
Yeah, exactly. Yeah. It's basically uniform, approximately uniform. It should say approximately uniform. I don't know why it says uniform compression, right? But we're basically looking at these, yeah. And those are the numbers that we get, 35 and 115. Cool. Oh, and both edges are supported because we have 2 edges which are unbuckleable, basically, right? That makes sense, yeah. So basically, yeah, before we do further calcs, we want to find the ratio of the element slenderness to the element slenderness yield limit. Okay. And the max one will govern for our entire section. So you see where it says E? E stands for element. That's like an individual component. And the worst case element is going to govern for our entire section.
What's worse, bigger or smaller?
Max. So a bigger ratio is worse.
Oh, max very good. Okay.
And then once we realize that element 1 governs, we're like, okay, we go back to the table. Oh, sorry. Firstly, we know what the section slenderness is. It's just going to become the element. The element slenderness is going to become the section slenderness, right? So it kind of adopts that value.
Yeah.
And same with the yield limit, the slenderness yield limit that we found earlier, right? Welcome back. And then, but then a new value from the table, which we didn't bother grabbing earlier, is the plastic slenderness limit. So that's from the same table, but we just go to the right. In that column, and we just unit that number, right? Oh, 30. Right. Oh, sorry. I highlighted the deformation limit. It should be plasticity limit. So the column to the left of the one that we, Okay. Here we have some rules. This is what's written in the lecture slides, I think. So I've done it like this way. But basically, it's like this. So our value that we got for the section slenderness is 32.53, right?
Yep, which is in between.
It's in between. So if it's in between these values, it's non-compact. If the value is less than here, if it's greater than the yield limit,
Slender.
It's slender.
Slender man.
Yes. And then if it's this way, it's compact, I believe. Let me double check that. Yes. So that's kind of how it goes. Right, you just compare these numbers on a number line. Yeah?
Yeah.
Okay. That's slenderness ratio done. Next we do moment of inertia. Right? And this is the easiest way to get Z. Right? Because
no parallel axis theory.
Yeah, exactly. Z is just this divided by d on 2. So if we just get this, right? It's pretty straightforward. If we have a rectangular hollow section, what we're doing is we're adding the moment of inertia of the big rectangle and then subtracting out the moment of inertia of the small rectangle. That's it. Right, so it's actually quite straightforward. So we have Z now, done. Okay, but the plastic section one is a little bit harder because we have to take the moment couple, right? So here it is, right? And it's gonna take a bit longer than the amount of time I'm gonna spend covering it at the moment to understand this fully. Like, it's good to just look at this diagram for long enough, basically, and then you'll get it, right? But the idea is that
Force times area.
your plastic moment, the moment couple that you do, is equal to the plastic section modulus multiplied by Fy. So if we're looking for this number, we have to first start with finding what MP is and divide out the strength. That's how it works.
Yeah.
So, and in order to find MP, we take the sum of the moments about the neutral axis for the case where everything's fully yielded. So that's why these are like rectangles, because they're fully yielded, right?
Oh.
Makes sense?
Oh boy.
Okay. Oh, and here I didn't even plug in what Fy was. It doesn't matter what Fy is because it cancels out. Yeah, everything cancels out. Yeah. Okay.
Okay.
Oh, any questions before we move on? Yeah. No. No. Okay.
Is there a term? Is this did we effectively find the moment of area?
Moment of area. So when you say moment of area, right? This is the first moment of area. This is the second moment of area, right?
Yeah, so we found the first moment of area without finding the fourth. Because we divide out Fy, which is the moment of force, so instead we just find the moment of area.
Because first moment of area is this, right?
Is what?
Is area multiplied by
Distance.
yes, and it's I think it's to each of these elements.
Yeah.
I'll have to think about that, but I don't know. I think it's better just to think of it like the plastic moment and you divide out the strength.
See, times the force and then divide the force. Okay, so okay.
I think because this one is in Newton meters, right? Or millimeters, Newton millimeters.
Mm-hmm.
This is in millimeters cubed, and this one's in newtons per millimeter squared. I think the first moment of first moment of area. Oh, I guess it is in millimeters cubed. Okay, I don't know. It could be. It could be. It's in similar units, but I don't know if it's the same thing.
Onwards.
Yeah. Okay, so there's different formulas, right? And this is the one that you pointed out was wrong before, but on the question is correct.
Yeah.
Yeah.
Yeah. That's good.
So to satisfy this formula, the first thing you have to do is find ZC. So that's what the section modulus, effective section modulus would be if it was a compact section. And it's a really simple formula. It's the minimum of what S, between S and 1.5 Z. Okay. And then once you find that, the rest is just plug in because we have all these numbers already.
Yep.
So it's actually quite straightforward.
Awesome.
Okay. Now we need to start working towards finding our components for MO, which is the reference buckling moment, right? And so the first one we have to do is moment of inertia about Y. So this one's slightly different because we basically swapped this. So before it was BD cubed on 12, and now it's B cubed D on 12 for the formula, like the IY formula, right? But
why are we finding this number?
Oh, because it's going to be used in this big formula later that we see for reference buckling moment.
Okay.
You'll see, basically. We're just prepping. We're prepping everything. We're getting all the geometric properties out of the way, custom geometric properties, so that we don't have to come back to it later. Reference buckling moment is going to be for member capacity. Oh, okay. So we're doing stuff for stuff way later down the line.
Okay, gotcha.
The section capacity stuff we've basically already done because we found ZE, and that's basically the whole thing.
Yeah.
So now we're prepping stuff for MB.
Okay.
Same thing with torsional constant, coefficient. So torsional coefficient, this formula is literally only for rectangular hollow sections. So Hamid just provided this formula in the assignment. And if they get you to do like a custom section for an assignment, they'll pretty much always give it to you because it varies so much shape to shape. You just plug it in and you get J. Okay. So now we can finally just, you know how you were talking earlier about how you bake? Or it's like Sue was talking about how you bake, and it's like you prepare all of the dishes, like everything in different bowls, right? And then you chuck it in all at once. That's what we're doing. So we just prepped everything in different bowls,
That's a good idea.
measured out like all your flour and your eggs and whatever.
That's a good way to do it.
Now we're literally just chucking everything together.
Yeah.
So we can easily find MSX because we found ZEX. We can now divide the beam into segments and subsegments, and like Sue mentioned earlier, there's symmetry. right? So you only have to worry about this part of the beam, so like the left half of the beam.
Mhm.
And then we just call this segment AB, right?
Yep.
Because remember the beam was ABC,
Yep.
and we've called this point with lateral restraint point D.
Yeah, I recall.
Okay, so we have segment AB, subsegment AD, and subsegment DB.
Three segments.
So basically, your lateral restraints will break up your segments into subsegments, but your full and partial restraints will break up the entire beam into segments. Does that make sense?
Why don't we have to do A to E?
A to E, oh, over here, if this was another lateral restraint.
Yeah.
Because these are restrained already.
Oh.
And you have to think about the function of why we're doing this. It's because we want to find effective length.
Oh.
And so there's no meaningful like physical thing behind finding AE. Because it has nothing to do with your effective length.
I see.
Because we think about what the length is of buckling. That's correct.
Interesting question. That was a good question.
Good question that you asked. It's like self-glazing. But yeah, okay.
Well, whoever asked it.
Someone asked it. Okay, let's think about this. Again, it's one of those things that I wish I would have more time to be able to explain. Because there's a lot to unpack with all the different scenarios. But you're just going to look at it hard enough at some point and figure it out. So basically, when you're trying to figure out the moment mod factor, there's two methods, right?
Mm-hmm.
Use the table or bending moment diagram. So we actually could have done the bending moment diagram version because we could have found, so if we go all the way back, right? Here I've done the graphical method for finding the bending moment diagram, right?
Yeah.
But what you could do is you could find it at 1/3 segment, at the first quartile, the second quartile, and the third quartile. Yeah.
Mm-hmm.
And then we can find alpha M using the formula, which uses like those quartiles and the moment max or whatever, right? I think it's like 1.7 moment max. We could have done that, but I just want to show you the other method basically, right? Because sometimes you are given a bending moment diagram that's like pretty cooked to be able to find those numbers, right? So you can do it this method. So this lays out a bunch of different scenarios in this table, but I've only just shown one here.
Mm-hmm.
So our bending moment diagram, this is from A to B, looks like this, right? Let me highlight it in yellow, this part here that I'm talking about. So we only care about this segment right now, right?
Mm-hmm.
Basically, we have to reverse engineer this, right? So what this graph is showing us, right? Again, just focus on the yellow because it's going to overwhelm you. The yellow part of the beam segment there on the left, that's our key, basically, right? It says the bending moment at that right-hand point is going to be equal to beta m WL squared on 8. That's it, right? And we have to reverse engineer it to find beta m.
What?
Yeah, it's fucking stupid. So we have to solve for beta m, right? So what I've done is I've just rearranged the algebra. Beta m is equal to 1.
So you need the real BMD.
You need that value. You don't need you don't need like the function, because you remember like
right.
Yeah, like m is a function of x is equal to
Yeah.
That one is better for like if you have that, it's better to use the other method. But if you just have that one value on the right, you can use this method.
Okay.
Yeah. Anyway, so we found beta m is 1. Cool. Okay, next we look at our range, right? Okay, so for this bottom range, which is when beta m is equal to 1 or from 1 to 0.7,
Mm-hmm.
we're allowed to use this formula.
Hell yeah.
And then we just chuck it in, right? And then this is what alpha m is. And it gives 2.25. So remember, this is going to be multiplied by to our capacity. So 2.25 means it's going to bolster our capacity or make it worse.
Effective left is extra long.
Not to do with the length.
Oh.
Because if the effective length was long, it's bad, right?
Yeah.
So remember, this is for MB. Is equal to MS times alpha M times alpha S.
Oh
right?
my god, this is good.
Yeah,
That's
exactly.
excellent.
But it can't be less. It can't be more than. It always gets rounded down to alpha to MS if this number's too OP basically. But since we're plugging it in here, this is going to make our bending capacity 2.25 stronger.
That's awesome.
Because of the moment redistribution, like it has a lot of area to
That's so good.
length to redistribute to. But the problem is alpha S will probably nerf it by quite a bit. So you have to see whether it's gonna how much it's gonna nerf it by.
Okay.
Which is what we're doing next, right? So next, effective length. So we have to do effective length for each subsegment now. So before we did alpha M for each segment, which is just the one, which is just A to B. Now effective length has to be for each subsegment. Okay. Am I going too quick, or does that make sense?
Wait, what's only once? The alpha M is once.
Once for this particular thing, yeah?
Yeah.
So let me show you this again, right? Because of symmetry, we only have one segment and two subsegments, yeah?
Yeah.
Alpha M was for the whole segment. That applies for the whole segment.
And the subsegments.
Because we'll do our calcs based on subsegments, yes. But we only have to calculate alpha M. So
we count it once and it counts for all segments.
Exactly.
And subsegments.
So this will be another alpha S value, and this will be another alpha S value. And when we multiply it together, we'll do this combination and this combination.
Oh.
So that alpha S, the alpha S of A to D, will be multiplied by the segment alpha M of A to B.
Gotcha.
Yeah, and then the same thing for the alpha S of segment DB to M. Okay, so now we're gonna do it based on subsegments because we're working towards alpha S, yeah.
Mm-hmm.
So this is the actual length, and then there's a few factors, right? This is a twist factor, and it's dependent on how many webs you have. So yeah, that one. Should I pull it up? Yeah, I think I should. So it's this twist restraint factor, right? But keep in mind, we have FL, right? FL is our restraint values. So if we go to our table, for FL cases, we always have a KT of 1. You see that in yellow?
L cases. Yeah.
So the effective length does not get increased for our twist restraint factor, yeah? Okay, but what about for PL, right? For PL, oops, that's future, yeah.
You got a little formula.
You have to do the formula.
Mm.
And that's to do with how many webs you have. So if you have one web, I think, actually just see how the maths goes. Basically you just try the formula. And what generally tends to happen is you have a number pretty close to 1, but you should still calculate it.
Okay.
Yeah, just to be fully correct.
That's cool.
Okay, that's KT. Sorry, we haven't talked about KL yet. The KL is the load height factor. This one's quite important because it will usually affect your calculations by like either 1.4 or 2. So it's making the length much longer than it actually is, right? Because we're assuming that the load is applied at the top flange, like that, right?
Oh,
that's the eccentricity thing.
That's too bad.
Yeah. So that really fucks with the effective length. And then it will depend on the restraint arrangement as well.
Oh, but this in this case, it's a top flange. In our question.
Yep. That's usually the assumption.
Yeah.
Unless it specifically says in the shear center. Because we have a UDL acting on top, right? Yeah, something on top, like squashing it down. So the load will be applied from the top flange. Okay, last is the lateral rotation restraint factor. This one's easy because at least Hamid said, we just assume it's... So if you have unrestrained, it doesn't really matter. Your KR factors 1. And you have something that's not unrestrained, you assume we have no ends with lateral rotational restraint. So basically KR is always 1. That's the assumption. So KR is basically always 1. Okay, and then so basically the thing that really just changed our effective length is our top flange loading, right? And it goes for both subsegments, right? Any questions? Okay.
No.
So basically, we just bumped up our length by 40%.
We just used the last week's.
Yeah.
formulas.
Yeah, exactly right.
Yeah.
Now here's the reference buckling moment. Now this formula is different to the one you saw last week, right? Because the one you saw last week is a little bit longer. Actually, I'll just show you it.
Oh my goodness.
Normally, when we're doing I-beams, we have to use that top formula. You see that, right?
Yeah.
That one's really long.
That's
But,
cool. But we're doing a rectangular hollow.
Yeah, exactly.
Ah.
We're doing a rectangular hollow section, which has a shorter formula because it's this one, right? But the thing is, since it's a custom section, it's really hard to get these values. You remember how we were calculating I, Y, and J?
Yeah.
That's what we prepped it for, right?
That's
But the thing is, if you're doing an I-beam, normally you can just yank these values from one steel. I, Y, I, W, yeah, these kind of things are quite easy.
Oh, we found them all.
Oh, G and E are always the same for steel.
Yeah.
So E is like 200,000 MPa.
Yep.
And G is 80,000. So that's your shear. First one's your elastic, or your Young's modulus, I guess. G is your shear modulus, I think it's called.
Mhm.
I'm just gonna rub this out because this is my good copy of the notes. Okay. But yeah, does that make sense? So, we still have to calculate both these reference buckling moments, right?
Mhm.
For the subsegments, because we're gonna still need alpha S for both subsegments.
Yeah.
So here I've calculated that
Alpha
one.
S is only for subsegments.
Yes.
And then a segment, alpha S is just 1.
No.
No.
It's about combinations, right? So, we're gonna marry these two, and we're gonna marry these two.
I see.
Yeah, do you see? So like, because MB is alpha S times alpha M times MS, right?
Yeah.
Yeah, we have to check it for, that and that. Oops. What the fuck? I'm gonna drag this down. Okay, so, yeah, we found the slenderness reduction factor by plugging all that shit in, basically.
Oh, so really we're only checking between the lateral supports.
Between the lateral supports.
Lateral restraints. So we never check A to B because it's a lateral restraint D.
Wait, say it again. Oh, that's the subsegment. That's for subsegments, right?
Yeah, so it
But
looks like we were checking 3, but really we are only checking 2, and segment AB is just a intermediate value.
But all the yes, because you're talking about LE, right? LE only cares about the subsegments,
Yeah.
yes.
But LE affects alpha S.
Yes.
So we only end up with 2 alpha S.
Yeah, exactly.
No, 3 alpha S.
Why 3 alpha S?
I don't know.
No, just 2.
Just 2?
Because if it's laterally restrained, right?
Mm-hmm.
Think about... I'm going to run 3D.
Yeah, 2, okay. Yeah, the L actually restrains it.
Yeah, it restrains it, so it does that, right?
Yeah.
Okay, this is Euler buckling. It's hard to draw what I actually want to draw, which is... That's lateral torsional buckling, right? Where only the top flange is doing weird shit. Right.
Okay.
So yeah. But you're right. The the lateral restraints do stop. Like it does break it up. Yeah, it does break it up. It's just the segments is where the moment's redistributed. Do you know what I mean?
Yeah.
So it kind of spreads out that moment. So that's why we have to do moment mod like that.
Right. So only need 2 alpha S. Okay.
Yes.
Okay. Yep.
Yeah,
and
makes
then we
sense.
find them, and then we do the calculations.
Mm-hmm. And then obviously the minimum moment capacity will govern. Right.
Yeah. But both of them are bigger than 1, so then you just reduce it back.
Both of them are bigger than 1. Oh yeah, that's
like
true.
alpha
Yeah.
M and alpha S.
Yeah, that's right. Yeah.
So you have to take it back to 220.
Yep. Because the moment redistribution factor is 2 OP basically.
That's so sad.
All that work for nothing. Yeah. Anyway, that was the first question, but I'll go over the second one very quickly.
Awesome.
So the only thing that changes is you just have to look at this in your own time, basically. The only thing that changes is we have a circular hollow section as well here.
No, that looks terrible.
It does look terrible, and
it's
just a different set of formulas, basically.
Hollow section with extra bits.
Yeah, with flanges, with not flanges, with just plates sticking out from all sides.
That's so bad.
No, but here's like the weird part, right? For circular hollow sections, they don't discriminate between how many edges are. Between like whether there's compression at one edge or tension at the other, or if it's uniform.
Yeah.
For circular hollow sections, you just need to know if it's heavily welded or not, pretty much. And so it's like that. But like I was saying last time, the slenderness yield limit is much higher for circular hollow sections.
Yeah.
Because and like rectangular hollow sections and stuff as well.
Yeah.
Because they're just much stronger in torsion. So that it's a higher threshold before they're considered slender.
Oh, I see.
Yeah, this is the yield limit.
Yield.
You have to make them really, really thin for them to be slender, to be considered slender. But yeah, makes sense.
Yep.
Yeah, and then you check which element governs. Element 3 in this case governs the one that's has uniform compression here. Wait, I don't know if did I do this right?
No, that's right. You just read the wrong thing. I think. Oh no, compression at one edge, zero stress in the other.
Yeah, it's more or less zero stress in the other, I think.
But it's compression.
But yeah, for these ones, this is uniform compression. I don't know, it's kind of a weird definition. It's like I don't know, but I got full marks in this assignment, so.
So the second one, it's like all compression, but it's a lot of compression.
Not really.
As in the range is quite a lot. The third one is basically zero.
Yeah, it's a bit weird. I don't know. Anyway, you just have to do your best to like pick the one that you think you can justify the best.
Yeah.
I don't even know if I like look back and think these definitions are correct, but I got 100 in the assignments for this, so I don't know.
I would have said the third one is compression at one edge, tension at the other.
Yeah, I feel like that's probably more accurate, eh? They're both kind of that. Oh, that's a bit weird. I don't know. Anyway. I think you could argue for either for this
Probably
one.
doesn't matter.
Yeah, it doesn't matter.
Probably not the one that governs.
But the third one's the one that governs, yeah.
Oh, it does matter.
Yeah, it does kind of matter. Anyway, whatever. But yeah. So it's non-compact again. But we're only finding MS, right? So we don't care about the bending moment diagram. We don't care about reference buckling moment. Alpha S, alpha M. That shit doesn't matter.
Yeah, instead of NB. Okay.
We're only finding MS, right?
No, yep.
Yeah, but remember, if you're doing a circular hollow section, the fucking calcs for moment is different. Oh, sorry, moment of inertia is different.
Yeah.
So you have to use this shit with pi and stuff, right?
Oh my goodness.
and parallel axis theorem shifting.
Oh my goodness.
This is why it's an assignment, right? and
Oh my
whatnot.
goodness.
Yeah. Like my handwriting's different here. This is because this is when I just got this tablet, so I'm not used to writing on it.
Oh my goodness.
Yeah.
This is a little
No, I couldn't be fucked to rewrite it. This is all just like additional information
Well,
and
it's better than my handwriting.
stuff. I'm not gonna disagree with that.
Kaden and Josh were complaining
Oh. Yeah. Okay, that brings me to the end. So.
Okay. Bye
Any questions?
everyone.
Bye,
Bye
folks.
YouTube.